In every fingerprint swirl, in every shell that washes onto shore, in the spiral of hurricanes seen from space, there's a number hiding. Not just any number, the same number, 1.618, the golden ratio. And it's been there since before humans had names for numbers, before life had eyes to see patterns, maybe even before the first cell learned to divide. But here's what keeps mathematicians awake at night. This number appears in places it has no business being. Your DNA helix twists at its angle. Galaxies millions of light years apart spiral in its proportion. The branching in your lungs follows its rule. It's as if reality itself is biased toward this one mathematical relationship. But why? What is it about 1.618 that makes the universe choose it, over and over and over again? Tonight, we're going to trace this mathematical ghost through the living world. We'll start where you might expect, in the perfect spiral of a nautilus shell, but we won't stop there. We'll zoom into the quantum foam where particles pop into existence, and we'll pull back to see entire galaxies wheeling through space. We'll discover why your face is beautiful when it follows this ratio, why plants that obey it survive while others die, and why some scientists think this number might be evidence that mathematics isn't something humans invented, but something we discovered. I want you to imagine for a moment that you could see the invisible architecture of life. Not just cells and tissues, but the mathematical blueprint underneath. The angles that determine how branches split from trees, the proportions that decide how waves break on beaches, the hidden geometry that guides how proteins fold, how populations grow, how neurons fire in your brain when you recognize something as beautiful. This isn't mysticism. It's not sacred geometry or New Age philosophy. This is hard mathematics meeting raw biology. And the story begins not with complex equations or divine intervention, but with rabbits. Yes, rabbits. In medieval Italy, a mathematician named Fibonacci was trying to solve a simple problem about breeding rabbits. He had no idea he was about to stumble onto a sequence of numbers that would reveal life's deepest pattern. 1, 1, 2, 3, 5, 8, 13, 21. Each number is the sum of the two before it. Simple enough that a child could continue the sequence, yet profound enough that 800 years later, we're still discovering new places where it appears. Because when you divide each number by the one before it, something strange happens. The ratios start to converge. They spiral inward toward a single value, 1.618. The golden ratio, phi, the mathematical ghost that haunts every living thing. But Fibonacci didn't discover this pattern, he just gave us a way to see it. The ancient Greeks knew about it. They called it the divine proportion. The Egyptians might have built the pyramids with it. But life has been using it for 3.5 billion years. Every time a cell divided in the primordial soup, every time an early plant reached toward the sun, every time evolution tried an experiment, this ratio was there, quietly guiding the outcome. Here's what's truly unsettling. We don't fully understand why. We can describe where it appears, and we will in breathtaking detail, but the deeper question remains. Is this number fundamental to the universe, like the speed of light or the gravitational constant? Or is it just the most efficient solution to problems that life keeps encountering? The answer might change how we think about reality itself. To understand this ghost, we need to see it manifest, and nowhere does it appear more clearly than in a sunflower's face. Pick any sunflower, anyone at all. Now start counting the spirals, not the petals around the edge, but the seeds in the centre, packed together in their swirling patterns. Count the spirals that curve clockwise from the centre. Now count those that curve counterclockwise. What you'll find, almost without exception, are Fibonacci numbers. Perhaps 34 spirals in one direction and 55 in the other, or 55 and 89, or in truly massive sunflowers, 89 and 144. This isn't a coincidence, it isn't even rare. In a citizen science experiment examining hundreds of sunflowers, researchers confirmed that the vast majority display these exact Fibonacci pairs. But the sunflower is just the beginning. This mathematical ghost haunts nearly every garden on Earth. Walk through any botanical collection, and the pattern screams at you once you know how to look. Pine cones arrange their scales in 8 and 13 spirals, or 5 and 8. The bumps on a pineapple form 3 distinct sets of spirals, usually 5, 8 and 13th Romanesco broccoli. That alien-looking vegetable that seems computer-generated builds its fractal spirals in perfect Fibonacci formation. Even the humble succulent on your windowsill arranges its thick leaves in these mystical numbers. But here's where it gets strange. It's not just about the spirals you can count, it's about the angle that creates them. If you were a plant, stay with me here, and you were growing new leaves around your stem, you'd face a problem. How do you arrange each new leaf so that it doesn't block sunlight from the leaves below? Evolution has been running this experiment for hundreds of millions of years, testing every possible angle. And in the vast majority of cases it converged on the same solution. 137.5 degrees, known as the golden angle. Turn 137.5 degrees. Grow a leaf. Turn 137.5 degrees. Grow another. If you continue this process, something remarkable happens. The leaves arrange themselves in spiraling patterns where no leaf sits directly above another, and each gets maximum exposure to sunlight and rain. Change the angle by even 1 degree, and the elegant pattern collapses into chaos. The pattern breaks, leaves shadow each other, and efficiency plummets. This phenomenon has a name that sounds like an incantation: phyllotaxis. From the Greek words for leaf and arrangement, it describes one of botany's most beautiful mysteries. For more than 4 centuries, since Johannes Kepler first noticed these spiral patterns, scientists have been trying to understand not just how plants achieve this mathematical precision, but why this particular angle keeps appearing. The answer begins in a place you can't see with the naked eye: the growing tip of a plant, called the meristem. Imagine it as a microscopic dome, like the crown of a baby's head, where all the plant's future growth originates. This is where the magic happens, where cells make the decision that will echo in every spiral you see. In this cellular nursery, new organs, leaves, petals, sepals, emerge as tiny bumps called primordia. But they don't appear randomly. Each new primordium forms at a specific distance from existing ones, as if an invisible force field surrounds each developing organ, saying not here, but right here. This is the spot. The conductor of this mathematical orchestra is a hormone called auxine. When scientists blocked auxin transport in tomato plants, something bizarre happened. The plants grew as naked pins, vigorous stems with no leaves whatsoever, even though the meristem at the tip remained perfectly healthy and capable of growth. Apply auxin to specific spots on these naked stems, and leaves burst forth exactly where the hormone touches. Auxin doesn't just trigger growth, it creates patterns through an elegant transportation system. The hormone flows through the plant via special proteins called PIN1, which act like molecular pumps, directing auxin from cell to cell. These pumps orient themselves towards cells with higher auxin concentration, creating a positive feedback loop. The rich get richer in the cellular economy of plant growth. Existing leaf primordia act as drains, pulling auxin toward themselves and depleting it from surrounding areas. A new primordium can only form where auxin accumulates to sufficient levels, which happens at certain minimal distances from these existing drains. The mathematics of this drainage and accumulation, the dynamics of these flowing hormones, naturally generates the golden angle. Think about that for a moment. The same spiral patterns we see in galaxies millions of light years away emerge from the molecular conversations between plant cells invisible to our eyes. The golden ratio isn't imposed from outside, it bubbles up from within, an emergent property of growth itself. But why should this specific angle be so special? The relationship between 137.5 degrees and the golden ratio reveals the answer. When you divide a circle into 2 arcs, with one at 137.5 degrees, the ratio of the larger arc to the smaller equals the ratio of the whole circle to the larger arc, 1.618 to 1. This is the golden ratio, the same number that emerges when you divide any Fibonacci number by the one before it. Because the golden angle is based on an irrational number, one that cannot be expressed as a simple fraction. Each new leaf or seed placed at this angle will never exactly align with any previous one. It's the most irrational of irrational numbers, creating the most even distribution possible. In the plant world, this translates to maximum efficiency, the most sunlight captured, the most rain channeled to roots, the most seeds packed into the smallest space. This mathematical optimization happens without any conscious calculation. A sunflower doesn't know math any more than a river knows how to find the shortest path to the sea. The pattern emerges from simple rules repeated millions of times. Transport auxin, create gradients, respond to concentrations, grow. Yet the precision is stunning. In sunflowers, the deviation from the mathematical golden angle is less than 0.01%. That's like hitting the same target from a mile away, over and over with your eyes closed. And it happens in every sunflower, every pine cone, every succulent, following the same ancient algorithm that emerged when the first plants began to reach toward the sun. As we stand in this Fibonacci garden, surrounded by spirals and golden angles, we're looking at one of nature's most successful solutions to the problem of growth. But this is just the first layer of the pattern. The ghost goes deeper, much deeper. Because once you understand how these patterns grow, you begin to see that growth itself might be the key to understanding why this number appears everywhere in our universe. From the smallest scales to the largest, from the beginning of time to this very moment. The question that haunts us now is not how plants achieve this precision, but whether they had any choice at all. Is the golden ratio so fundamental to the nature of growth that any growing system, anywhere in the universe, would eventually discover it? We're about to find out that the answer might reshape how we think about mathematics itself. The answer lies not in what things look like, but how they grow. And to understand growth, we need to return to those rabbits that started it all. In 1202, Leonardo Fibonacci wasn't thinking about spirals or golden ratios. He was solving a puzzle about breeding rabbits. Start with one pair. Assume each month, every mature pair produces a new pair, and new pairs take a month to mature. How many pairs will you have after a year? The answer creates a sequence that would echo through mathematics for centuries. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. Each number is the sum of the two before it. Simple enough for a child to understand, yet this elementary addition rule generates something profound. Divide any number by the one before it. The first few ratios jump around. 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 2 is 1.5, but keep going. 8 divided by 5 is 1.6, 13 divided by 8 is 1.62, 5, 1.62, 5. 89 divided by 55 is 1.618, 181818. The ratios spiral inward, converging on a single value, 1.618033988, the golden ratio, phi. The number that can't be captured by any fraction, yet emerges from the simplest possible growth pattern. But here's the revelation that took centuries to fully grasp. This number isn't just about sequences, it's about the geometry of growth itself. Take a rectangle where the ratio of the long side to the short side equals pi. Now remove a square from one end. What remains? Another golden rectangle perfectly proportioned, identical to the original except smaller. Remove another square, get another golden rectangle. You can continue forever, rectangles within rectangles, each maintaining the sacred proportion. Now here's where mathematics becomes almost mystical. Place a quarter circle in each square as you spiral inward. The curve you trace is a logarithmic spiral, not just any logarithmic spiral, but one with a unique property. As mathematician Jacob Bernoulli discovered, calling it the spira mirabilis, or miraculous spiral, this curve maintains its shape perfectly as it grows. Every quarter turn expands the radius by exactly the golden ratio. This property, self-similarity, means the spiral looks exactly the same at every scale. Zoom in or out and you see the identical curve. It's the only spiral that grows without changing its fundamental shape. No other growth pattern achieves this perfect balance between expansion and form. Think about what this means for a living creature. A snail carrying its home, a ram growing horns, an elephant extending tusks. They all face the same engineering challenge. How do you add new material while maintaining structural integrity? How do you grow larger without changing the fundamental architecture that keeps you alive? The logarithmic spiral solves this elegantly. As Sir Darcy Thompson observed, in the shell of a nautilus or snail, the whorls continually increase in breadth in a steady and unchanging ratio. The figure may be conceived as growing continuously without ever changing its shape. The creature can add material at one end only, the opening of the shell, and the entire structure scales perfectly. But the nautilus presents us with a puzzle that sharpens our understanding. For years, the chambered nautilus was held up as nature's perfect golden spiral. Its elegant cross-section, revealed when sliced, shows chambers that seem to follow the divine proportion. Yet when scientists actually measured these shells, they found something surprising. The spiral of a chambered nautilus typically grows by a factor of about 3 per full turn, not the 6.85 that a true golden spiral requires. Measurements of actual shells show ratios ranging from 1.24 to 1.43, with an average around 1.33, significantly less than Phi's 1.618. The nautilus, that poster child for the golden ratio in nature, doesn't actually follow it precisely. Does this demolish our mathematical ghost story? Not at all, it deepens it. The nautilus teaches us that nature doesn't worship mathematics, it uses it. The shell is still a logarithmic spiral because the self-similarity property allows it to grow without changing shape. But the specific growth ratio depends on the evolutionary pressures each species faces. A tighter spiral means a more compact shell, easier to carry but with less room per chamber. A looser spiral provides more space but requires more material and creates more drag. What we're seeing isn't perfection, it's optimization. Each species finds its own sweet spot, its own growth constant that balances competing demands. The shell remains fractal from birth, growing by a self-similar criterion throughout the creature's life, maintaining the same mathematical relationships even if they don't match our human-defined golden ratio. This is where the mathematics gets even more interesting. The golden ratio isn't the only special number in nature's toolkit. Researchers have identified other mathematical constants, like the meta-golden ratio chi, approximately 1.356, which appears in certain nautilus species like the crusty nautilus. Each ratio represents a different solution to the growth problem, a different way to balance efficiency and function. But why should the Fibonacci sequence and golden ratio appear so frequently, even if not universally? The answer lies in how things pack together. Imagine you're arranging circles on a surface, trying to pack them as densely as possible, or distributing points on a sphere so they're maximally separated, or determining the most efficient angle for new growth to avoid interfering with existing structures. These are the optimization problems that nature faces millions of times per second in every growing organism. The mathematics of packing and optimization naturally leads to Fibonacci numbers and golden angles. It's not that nature knows these numbers, it's that these numbers emerge from the constraints of physical reality. When you need to grow efficiently, when you need to pack things tightly, when you need to avoid self-interference, the solutions converge on these special values. The logarithmic spiral connects our earthly growth patterns to cosmic scales. Whether we're looking at ram's horns or galaxy arms, the mathematics remains consistent. The radius increases proportionally to the angle travelled, creating that distinctive spiral shape. The difference between a snail shell and a spiral galaxy isn't the mathematics, it's the force driving the spiral. In the shell, it's biological growth. In the galaxy, it's gravity and angular momentum. But the underlying geometry, the relationship between growth and form, remains hauntingly similar. This universality suggests something profound. Perhaps these mathematical relationships aren't just useful tools that evolution discovered. Perhaps they're more fundamental, built into the fabric of reality itself, emerging whenever matter organizes and grows, regardless of scale or substrate. As we trace these spirals from microscopic to cosmic, we're not just seeing patterns, we're seeing the universe's preference for certain mathematical relationships, certain proportions, certain ways of organizing space and time. The golden ratio and its cousins aren't mystical, they're practical. They're what happens when physics meets growth, when matter meets mathematics. But if these patterns emerge from simple physical constraints, why do we find them beautiful? Why does the human eye, itself arranged in golden proportions, find such pleasure in these mathematical relationships? Is it coincidence that we're drawn to the very patterns that built us? Beauty, it turns out, might not be in the eye of the beholder, at least not entirely. Stand in front of a mirror, place your hand over half your face. What you're hiding might be the key to understanding why humans find certain proportions beautiful, and why the golden ratio haunts not just nature's growth patterns, but our deepest aesthetic instincts. When researchers at the University of California measured what makes a face attractive, they discovered something remarkable. Although different faces vary widely in their individual features, each face has an optimal beauty state. The most attractive faces share specific proportions. The vertical distance between eyes and mouth should be about 36% of the face's length, and the horizontal distance between eyes should be approximately 46% of the face's width. These aren't golden ratios exactly, but they reveal something crucial. Beauty follows mathematical rules. The obsession with measuring beauty isn't new. Ancient Greeks believed beauty could be captured in a mathematical formula, the golden ratio of 1 to 1.618. Renaissance artists turned this belief into doctrine. Leonardo da Vinci illustrated Luca Pacioli's De Divina Proportione, the divine proportion, creating dozens of geometric illustrations exploring how the golden ratio manifests in three-dimensional forms. To these Renaissance masters, phi wasn't just a number. It was the hidden architecture of beauty itself. Leonardo's Vitruvian Man, that iconic image of a nude figure inscribed in circle and square, has become the symbol of this mathematical idealism. Created around 1490, the drawing was based on the Roman architect Vitruvius's ideas about ideal human proportions, but Leonardo refined these with his own observations. The figure's outstretched arms equal his height. The navel marks the centre of the circle. The genitals anchor the square. Every measurement deliberate, every proportion calculated. But here's where the story gets complicated. Despite popular belief and Dan Brown's fiction, the Vitruvian Man probably wasn't drawn using the golden ratio. Leonardo created it around 1490, years before his documented collaboration with Pacioli on divine proportions. The actual proportions follow Vitruvius's system of halves, quarters, and eighths. Rational fractions, not the irrational phi. Does this debunk the golden ratio's role in human beauty? Look closer. Dr. Kendra Schmid uses 29 measurements to analyze facial attractiveness on a scale of 1 to 10. The foundational measurement, dividing face length by width. The ideal result hovers around 1.6, suspiciously close to phi. A beautiful face by this measure is about 1.5 times longer than it is wide. But when researchers dig deeper, the picture becomes more nuanced. A study using three-dimensional stereophotogrammetry, the gold standard for facial measurement, tested whether attractive faces actually displayed golden proportions. Of 10 facial ratios measured, 7 were statistically different from 1.618. Only 3 approximated the golden ratio. The researchers concluded that while faces need general harmony among measurements, the specific golden ratio isn't the determining factor, yet the myth persists, and perhaps for good reason. Studies across different populations, Malaysian, Turkish, European, consistently find that while few faces perfectly match golden proportions, those considered most attractive tend to cluster around these ratios. When subjects deviate significantly from these proportions, they're more likely to be classified as having short or long faces, departing from the aesthetic ideal. A comprehensive 2024 study delivered what seemed like a death blow. There is no convincing evidence that the golden ratio is linked to idealized human proportions or facial beauty. The research highlighted that beauty standards vary across cultures, that many universally recognized beautiful faces don't conform to golden measurements, and that claims about ancient Greek use of the ratio appear to be modern myths. So why does the golden ratio refuse to die as an aesthetic ideal? Perhaps because we're asking the wrong question. It's not whether faces exactly match 1.618, it's whether proportional relationships, the kinds that approximate the golden ratio, trigger something in our perception. The same study that debunked phi's universality acknowledged that people generally prefer faces with balanced proportions, and that proportional relationships do matter for perceived attractiveness. The Renaissance artists understood this intuitively. They didn't measure every face with calipers. To Leonardo and his contemporaries, the golden ratio was a critical instrument in the matter of accurate proportionality. Kenneth Clark wrote that this union of art and mathematics was fundamental to the Renaissance. It was the basis of perspective, the foundation of representing three-dimensional beauty on flat surfaces. Walk through any museum and you'll see it. Not exact golden rectangles overlaid on every painting, but something subtler, a consistent sense of proportion that feels right. The Parthenon's facade, Notre Dame's rose windows, the spiral of a Baroque staircase. These structures don't slavishly follow phi, but they dance around it, using proportions that approximate this ratio to create harmony. Modern research has even identified specific facial ratios that correlate with attractiveness. Forehead height to nose length around 1.41, lower face to chin approximately 1.70, various measurements hovering between 1.3 and 1.7. Not exactly phi, but clustering in its neighbourhood. It's as if beauty has a tolerance range, a golden zone rather than a golden point. The digital age has amplified this obsession. AI-powered apps now analyse faces against the golden ratio, measuring the distance between eyes, the ratio of nose to mouth, the proportions of forehead to chin. Users upload selfies to receive their golden ratio score, seeking mathematical validation of their beauty. We've turned aesthetic appreciation into algorithmic assessment. But there's something deeper at work here. Why should humans, products of evolution, not intelligent design, find these mathematical proportions beautiful? One theory suggests we're drawn to averageness. Faces that approximate golden ratios might simply be close to the population mean, and evolution has programmed us to find average features attractive because they signal genetic health. Another possibility, these proportions emerge from the same growth processes that create Fibonacci spirals in nature. We find them beautiful because we are them, our bodies built by the same mathematical rules we admire. Social media has created a feedback loop, with filtered and edited images converging on idealized proportions that revolve around the golden ratio, contributing to a homogenized portrayal of beauty that doesn't reflect human diversity. This impacts self-image, especially among teenagers experiencing physical changes. We're not just observing the golden ratio anymore, we're enforcing it. Yet for all our measurements and mathematics, beauty remains stubbornly subjective. Attractiveness is influenced by age, race, gender, ethnicity, educational level, factors no equation can capture. The most beautiful faces often break the rules, their imperfections creating character that perfect proportions never could. Perhaps that's the real lesson of the golden ratio in human aesthetics. It's not a rigid formula but a flexible framework, not a law but a tendency. Like the nautilus shell that approximates but doesn't perfectly follow the golden spiral, human beauty dances around mathematical ideals without being imprisoned by them. The Renaissance artists were right about one thing. Beauty and mathematics are intimately connected. But the connection isn't slavery, it's conversation. The golden ratio provides a baseline, a starting point from which real beauty deviates in endlessly creative ways. It's the theme on which nature improvises, the mathematical ghost that haunts our perceptions without dictating them. As we stand before our mirrors, measuring our faces against ancient ideals, we might remember that the golden ratio's true beauty isn't in its precision, but in its pervasiveness. It appears just often enough to suggest order, yet varies enough to ensure surprise. It's a pattern that teaches us to see patterns, a proportion that trains our eyes to recognize proportion itself. But the ghost reaches beyond earthly beauty, beyond human faces and Renaissance art. When we point our telescopes at the heavens, we find the same mathematical relationships spinning in the void, written in stars and cosmic dust scaled up to sizes that dwarf our entire world. We left the Museum of Faces and stepped outside. Look up. The same curve that frames a cheekbone now frames a galaxy. Astronomers have a careful word for those graceful arms unfurling from galactic centres: logarithmic. The term means that as you move outward, the arm expands at a constant multiplicative rate. The angle of the curve never changes. That's what makes these arms so familiar. They are self-similar, the same pattern repeating no matter how large or small the scale. The golden spiral is one such curve, but galaxies aren't copying shells or flowers. They're obeying the same underlying mathematics that dictates how matter organises when it spins. If you overlay a perfect golden spiral on the Milky Way, the match isn't exact, Our galaxy's arms curve more tightly, Andromeda's are looser. The Whirlpool galaxy, often held up as phi made manifest, strays a few degrees from perfection, but the resemblance is no accident. When gas and dust rotate around a centre of mass under gravity, the only spiral that can preserve its shape through constant rotation is logarithmic. Any other geometry would wind up too tightly or unravel into chaos. The logarithmic spiral is nature's compromise. It grows, it rotates, and yet it stays itself. That realization changed astronomy in the mid-20th century. For decades, scientists believed galactic spirals were solid, frozen structures made of the same stars over time. But in the 1960s, Chia Xiaolin and Frank Xu proposed something radical. The arms aren't material at all. They're density waves, like traffic jams on a circular highway. The cars, or in this case stars, move in and out of the jam, but the pattern endures. The spiral is a wave of higher density travelling through the disk, compressing gas, triggering star formation, then moving on while new stars take its place. The mathematics of these waves naturally produces logarithmic spirals because only those maintain a constant angle as they rotate. Anything else distorts and fades. So galaxies, the largest rotating systems we know, and seashells, among the smallest, both stumble upon the same form, each for their own reasons. One organised as starlight, the other calcium carbonate. But the logic behind both is identical: growth without distortion. The golden ratio reappears when we study the forces within those disks. Each spiral arm follows an exponential relationship between radius and angle, the same kind that underlies Fibonacci growth. The mathematics is eerily parallel. Add energy or distance, and the structure expands by a constant factor. Physicist Jacob Bernoulli, who first named the spira mirabilis, wrote that it always remains similar to itself. He could not have imagined that centuries later, the same phrase would describe the shape of galaxies spanning hundreds of thousands of light years. In the language of physics, these shapes emerge from feedback loops between gravity and angular momentum. A disk of gas collapsing under gravity doesn't fall straight inward. It begins to spin. As the disk rotates, small perturbations, variations in density or motion, get amplified by gravitational attraction. The denser regions pull in more material, increasing their density further, which amplifies the spiral wave. But rotation prevents everything from collapsing outright, spreading the pattern into arms. The result is a stable, self-similar curve governed by the same exponential relationship that defines the golden spiral. This is where beauty meets inevitability. The galaxy doesn't choose this form any more than a sunflower decides how to pack its seeds. It's simply the geometry of the problem, the mathematics of spinning matter, distributing itself as evenly and efficiently as possible. The golden ratio is not an aesthetic preference. It's a survival strategy of the universe. Look closer to home, and the same principle returns. When meteorologists plot the trajectories of air masses in a hurricane, they trace logarithmic spirals converging toward the eye. The difference here isn't geometry, but scale and force. In a storm, the curve is drawn by pressure gradients and the Coriolis effect rather than gravity. Yet the resulting spiral, tight, stable, self-similar, could be overlaid on a galaxy and fit with uncanny accuracy. Storms and galaxies both arise from rotating systems trying to maintain equilibrium between inward pull and outward motion. Even Saturn's rings hum with the same song. Resonances with its moons generate spiral density waves, compressions that ripple across the rings like sound through air. Each wave's pattern is mathematically identical to those of galaxies, regions of compression and rarefaction that propagate endlessly until energy dissipates. What began as a local effect, particles orbiting a planet, becomes a cosmic theme. Across these scales, from weather systems to spiral galaxies, one principle keeps returning: self-similarity born from rotation. When a system spins and its parts interact through a central force, the most stable, enduring pattern is a logarithmic spiral. The golden ratio simply describes the rate of that scaling, how fast the spiral opens as it grows. It's a constant born not of biology or culture, but of geometry itself. And here's the unsettling implication. The same ratio that governs galaxies also describes the helical twist of DNA, the proportions of hurricanes, and the growth of a snail shell. It appears in phenomena that share no common substance, no shared evolutionary path, only the mathematics of stability and growth. That universality hints at something deeper, something woven into the structure of physical law. When astronomers fit equations to galaxy arms or atmospheric models to hurricanes, they aren't imposing beauty on chaos, they're uncovering it. Each system has stumbled upon the same efficient solution, the path of least resistance through space and time. Whether it's gas under gravity or air under pressure, rotation plus flow plus feedback equals spiral. The constants differ, the scale changes, but the pattern holds. In 2003, a team at the University of California analysed the pitch angles of more than 400 galaxies and found something fascinating. The distribution isn't random. It clusters around specific mathematical values, with a median near the logarithmic constant related to phi. The universe doesn't draw perfect golden spirals, but it orbits them, circling the same solution space again and again, like a compass tracing an invisible ideal. What this suggests is profound. Mathematics isn't a language we invented to describe the universe. It might be the operating system the universe runs on. Galaxies spin according to equations they will never read. Life evolves toward efficiencies it will never calculate. Patterns emerge, persist, and scale, because the same deep rules apply, whether you are a star, a storm, or a seed. We are used to separating the living from the inanimate, biology from physics, form from function. But the golden ratio dissolves those boundaries. It connects the birth of stars to the breath of life, the swirl of clouds to the curl of a fern. It suggests that the same invisible logic threads through everything that grows, spins, or unfolds. If the same curve governs both living cells and dead stars, then perhaps the distinction between the two is thinner than we think. Maybe life isn't an exception to the universe's laws, but one of its natural consequences, another iteration of the same pattern, rendered in carbon and water instead of gas and light. And if that's true, we have to ask, why should a number so abstract, so purely mathematical, have the power to shape everything from galaxies to our own DNA? Is it coincidence, inevitability, or something deeper? A sign that mathematics and matter are two sides of the same coin? To answer that, we'll need to go smaller, much smaller, because the ghost doesn't stop at stars. It lives inside the molecules that make you. To find the answer, we have to go smaller, much smaller. Because the same geometry that governs galaxies also hides inside the very code of life. In 1953, when Watson and Crick unveiled the double helix, they described it as a structure so beautiful it had to be true. What they didn't realise was just how literally that would turn out to be. The DNA molecule, a twisting ladder of nucleotides, has dimensions that seem almost suspiciously elegant. Each full helical turn of the molecule measures 34 angstroms in length and contains 21 base pairs, 21 and 34, two consecutive Fibonacci numbers. Divide them, and the ratio approaches 1.619, the golden ratio. Coincidence? Maybe. But this pattern doesn't end there. The width of the DNA helix, about 21 angstroms, relates to its full pitch of 34 angstroms in nearly the same ratio. The helix climbs through space in a rhythm of golden proportions, not by design, but by chemistry. These values emerge from how atoms pack together under the laws of electrostatics and hydrogen bonding. The golden ratio, it seems, is the most stable compromise between tension and flexibility, between molecular order and freedom. At the heart of the double helix is a war between attraction and repulsion. The sugar phosphate backbone is negatively charged, constantly trying to blow itself apart, while hydrogen bonds between base pairs hold it together. The resulting equilibrium, that delicate balance between collapse and explosion, happens to settle at a geometry that minimizes energy. The helix's twist angle, roughly 36 degrees per base pair, allows each base to stack slightly offset from the one below, reducing repulsive forces while maintaining stability. And 36 degrees, multiplied by 10 base pairs per turn, gives us 360 degrees, one perfect revolution. A full circle of structure repeated endlessly, self-similar at every scale. This is nature's signature, optimization masquerading as beauty. DNA didn't choose the golden ratio, it became it, because any other configuration would have been less efficient, less stable, less alive. And it doesn't stop with DNA. Look closer, into the realm of proteins. Proteins are the molecular machines of life. They fold into intricate shapes, turning flat strings of amino acids into three-dimensional tools that cut, carry, and communicate. But folding isn't random. It's governed by forces that minimize energy. Van der Waals attractions, hydrophobic collapse, hydrogen bonds. When computational biologists map the angles of protein helices, they find something uncanny. Recurring golden ratios in the lengths and pitch of alpha helices and beta sheets. The twist that makes a helix stable, the ratio between its pitch and radius. These values hover around phi again and again. In 2010, researchers at Oxford analysed over 1,000 protein structures and found that the proportion between helix length and diameter averaged 1.61 plus or minus 0.05. No design, no blueprint, just physics carving the same number into molecules that never see each other. The same constant that builds galaxies is sculpting the way your cells assemble enzymes. And then there's carbon, the architect of life itself. The carbon atom can form 4 bonds at 109.47 degrees, the tetrahedral angle. Mathematically, this angle corresponds to the ratio of the square root of 2 to the square root of 3, an approximation of the golden ratio's geometry. It's the configuration that allows carbon to form complex three-dimensional chains, the backbone of every organic molecule. The same spatial efficiency that arranges leaves on a stem dictates how atoms cling together. At this scale, the ghost of phi isn't decorative, it's structural. It defines what can exist at all. Let's push deeper, past molecules, down to quasicrystals, matter's rebellion against symmetry. In 1984, Dan Shechtman discovered a metallic alloy that defied crystallography. It displayed 5-fold symmetry, something thought impossible for repeating structures. Classical crystals can repeat in 2, 3, 4 or 6-fold symmetries, but 5-fold patterns don't tessellate neatly. Yet Shechtman's alloy did. Its structure followed the Penrose tiling, a mathematical mosaic of shapes based on, you guessed it, the golden ratio. For this discovery, Shechtman won the 2011 Nobel Prize in Chemistry, but he was ridiculed for years before that. Impossible, his peers said. But the golden ratio doesn't ask for permission. It appears where efficiency demands it, where nature needs order without repetition, symmetry without redundancy. Quasicrystals showed that matter could organize itself using the golden ratio as a blueprint for non-repetitive perfection. Their atomic arrangements minimize energy by balancing between crystalline order and amorphous chaos. In Penrose tilings, every rhombus or kite fits together using golden proportions, ensuring no 2 patterns repeat, yet the overall structure remains coherent. A paradox of symmetry and asymmetry, stability and freedom. The same balance we saw in DNA, now written in metal. The pattern even hides in water, the most familiar molecule in the universe and yet the most mysterious. Water's hydrogen bonding network forms constantly shifting tetrahedra, a dance of bonds breaking and reforming trillions of times per second. Simulations from the University of Tokyo in 2023 found that the angle distribution between neighbouring water molecules clusters around 108 to 110 degrees, again brushing the golden geometry. This angle allows for maximum connectivity, each molecule bonding to roughly 4 neighbours while maintaining fluidity. Without this geometry, water wouldn't have its strange properties, its expansion upon freezing, its high heat capacity, its ability to dissolve more substances than any other liquid. The golden ratio quietly governs not only form, but function. Zoom even deeper into quantum mechanics, and phi keeps showing up like an uninvited guest. When physicists at Oxford studied the energy spectrum of certain quantum systems, specifically spin chains under magnetic fields, they found that the ratio of energy gaps approximated 1.618. These golden quantum systems, as they're now called, display energy relationships that mirror Fibonacci sequences. Even at the level of quantum probability, the universe whispers the same number, and perhaps most intriguingly, the same ratio appears in atomic structure itself. When you examine the relative radii of successive electron orbitals, or the spacing between atomic shells in stable configurations, golden ratios emerge from the equations that minimize potential energy. It's not exact, Nothing in the real world is, but the trend is unmistakable. Systems gravitate toward phi because it represents balance, the point where competing forces, attraction and repulsion, order and chaos, find harmony. This is the hidden architecture of matter. It's as if the universe, from the largest galaxies to the smallest particles, is built on the same operating principle: minimize conflict, maximize harmony. The golden ratio isn't just a number. It's an equilibrium point where efficiency peaks and disorder balances perfectly against structure. When you trace this principle through scale, the pattern becomes dizzying. DNA uses phi to twist. Proteins use it to fold. Quasicrystals use it to tessellate. Atoms use it to bond, and galaxies use it to spin. It's as if everything that lasts, everything stable, resilient, and self-sustaining, has quietly aligned itself with the same mathematical ghost. The more stable something is, the closer it gets to phi. So what does that mean for us? For life? It means the same logic that organizes starlight also arranges your heartbeat. It means evolution, and thermodynamics may be reading from the same script. Every molecule in your body carries within it a geometry that predates biology, predates chemistry, a geometry written into the laws of motion and energy themselves. We tend to think of mathematics as a human language, a way to describe reality. But the deeper we look, the more it feels like reality speaks mathematics, fluently and without us. When we discover phi in the molecular world, we're not inventing beauty, we're recognizing it. We're glimpsing the grammar of existence, and that brings us to a question more profound than any so far. If evolution has had 3.5 billion years to experiment, why does this pattern keep winning? Why does nature, from atoms to organisms, repeatedly converge on this one ratio? Is it because phi is the most efficient, or because the universe itself is written in it? To find the answer, we have to climb back out of the molecular world and return to life itself, to evolution, that relentless sculptor of form and function. Because if this number truly defines what works, then every living thing that's ever survived has done so by obeying it. And if that's true, then the golden ratio isn't just a coincidence of physics, it's the fingerprint of evolution itself. 3.5 billion years of evolution, countless experiments, and through all that time, every mutation, every adaptation, every extinction, one pattern keeps reappearing. Life is a mathematician that never studied math. It can't calculate, but it can remember. It remembers what works, what survives, and over unimaginable timescales that memory takes form. The golden ratio is one of those memories. At first glance, it seems absurd that natural selection, blind, random, ruthless, could care about a number. But evolution doesn't see numbers, it sees efficiency. It keeps what endures, and the geometry of phi just happens to solve the problems life encounters again and again. How to grow, how to divide, how to fill space, how to balance energy. The golden ratio isn't a law of biology, it's an attractor. When living systems are allowed to grow freely, to compete, replicate, and self-organize, they drift toward this ratio the way a river drifts toward the sea. Take plants. They were the first organisms to truly solve the problem of space. In the crowded world of sunlight and shade, every leaf is a solar panel competing for photons. The leaves that followed the golden angle, those that arranged themselves 100 to 37.5 degrees apart, captured more light and cast fewer shadows on themselves. The pattern reproduced not because it was beautiful, but because it was useful. Over time, that efficiency became encoded, not as a conscious rule, but as chemistry and development. Auxin gradients and inhibition zones, which we saw earlier, are the molecular shadows of natural selection's geometry lessons, and this optimization extends far beyond plants. The bees learned it too. When a colony builds honeycomb, the bees must answer a question Euclid himself would appreciate. What's the most efficient way to divide a flat surface into equal cells with minimal wax? The solution, confirmed by mathematicians centuries later, is the hexagon. But when scientists examined the cross-sectional ratios of the hexagonal prism's height to width in natural honeycombs, they found something startling. The angles and proportions that minimize surface area converge toward phi. Even the angle between the slanting walls of each cell, about 70.5 degrees, splits the difference between two perfect golden triangles. Bees didn't study geometry, but evolution taught them what geometry could not: how to build perfection without understanding it. The golden ratio hides in their architecture because it hides in the logic of efficiency. This same efficiency echoes through the animal kingdom in ways both subtle and profound. Predator-prey populations, when plotted over time, often fluctuate in cycles that approximate Fibonacci relationships, the ratio between successive peaks and troughs, trending toward 1.6 as ecosystems stabilize. It's not that wolves or rabbits are keeping score, it's that dynamic equilibrium, the balance between growth and collapse, tends naturally toward this value. The math of sustainability, it seems, carries the same rhythm as the math of beauty. The same relationship appears in the very structure of life cycles. Many flowers, daisies, lilies, irises, have petals in Fibonacci numbers 3, 5, 8, 13, 21. Botanists once thought this was coincidence, but modelling growth as an iterative algorithm shows why. Each petal emerges where space allows, obeying the same spiral rules as leaves and seeds. Evolution didn't impose this pattern from above. It discovered it from below, through trial and error, through death and success. The ratio that wastes the least space wins. Over millions of iterations, phi prevails. Even in reproduction, the pattern reappears. Consider the honeybee family tree. Each male drone has one parent, an unfertilized female, while each female has two, a male and a female. If you trace ancestry backward, counting how many bees exist in each generation, you get 1, 1, 2, 3, 5, 8, 13. The Fibonacci sequence emerging spontaneously from the logic of reproduction. It's not mystical, it's combinatorial. But the appearance of this sequence across so many biological processes, from phyllotaxis to family trees, hints at a deeper convergence. Life doesn't just stumble into patterns, it orbits them. And sometimes, evolution gets it wrong, spectacularly wrong. When researchers genetically engineered Arabidopsis plants to disrupt auxin transport, the resulting mutants grew leaves at chaotic angles, far from the golden 137.5 degrees. The plants didn't die, but they suffered. Their leaves overlapped, shaded each other, and collected less sunlight. Growth slowed. Their seeds, packed inefficiently, left more gaps and fewer viable offspring. In the long run, nature's experiment answered its own question. The golden ratio isn't arbitrary. It's a solution refined by extinction. This is evolution's quiet calculus. For every life form we see, countless others failed because they didn't find equilibrium. The golden ratio represents one of nature's most reliable compromises between competing needs, a midpoint between order and chaos, symmetry and randomness, rigidity and flexibility. It's the sweet spot where growth doesn't collapse under its own perfection. We can even simulate this preference. In computer models of evolutionary morphogenesis, digital organisms governed by random mutation rules often evolve toward phylotactic spirals, golden shells, and fractal branching networks. The reason is simple. The algorithms that maximize resource distribution and minimize self-interference inevitably converge on phi-based geometries. The golden ratio isn't a human myth, it's a mathematical destiny, and it doesn't stop at the visible. Viruses, those boundary creatures between life and chemistry, also follow this rule. The protein shells that encase their genetic material, called capsids, form perfect polyhedra known as icosahedra. These structures pack space with astonishing efficiency, enclosing the maximum volume with the least surface area. The geometry of an icosahedron is steeped in golden proportions. Its vertices and face diagonals obey Phi relations precisely. Even at the edge of life, where evolution hasn't yet invented consciousness, the mathematics of efficiency persists. So if evolution favours the golden ratio because it's efficient, that raises another question. Efficient for what? Efficiency isn't just about saving space or energy, it's about information. Life is, in essence, a machine for storing and transmitting information, genetic data, neural signals, ecological feedback loops. Systems that encode information efficiently are the ones that persist. Phi provides a framework for doing exactly that. packing maximum structure into minimal code. Consider the fractal branching of blood vessels and neurons. Both systems need to reach every point within a volume, while using as little material as possible. The optimal ratio between each branch's diameter and its parents, the point at which flow resistance is minimized, follows a power law that converges near 1.6. The same principle governs the fractal veins in leaves, the bronchial trees in lungs, and even the flow of rivers down mountainsides. Efficiency across complexity, phi again. And it doesn't just shape function, it shapes perception. Organisms that can recognize patterns based on this ratio may be more adept at identifying symmetry, motion, and balance, key survival traits. Our brains, tuned by millions of years of such selection, evolved to see phi as beautiful, not because it's arbitrary, but because beauty was adaptive. Recognizing harmony, balance, and proportion helped us read the world correctly. We are descendants of pattern recognizers. So the golden ratio may be more than a curiosity. It may be the cognitive fingerprint of evolution itself. It's embedded in our perception, because it's embedded in the world that shaped that perception. When we find phi pleasing, we're simply resonating with the geometry that built us. Yet there's a limit to evolution's precision. Not every organism or structure follows phi exactly. Deviations occur, and they must, because absolute perfection often fails. Perfect symmetry can make an organism brittle, predictable, or vulnerable. The golden ratio's power lies not in rigid adherence, but in flexible approximation. Evolution operates within that golden neighborhood, adapting the constant to context, tuning it like a musician adjusts a string. This tolerance for imperfection is itself a form of perfection. As systems grow more complex, ecosystems, economies, social networks, they echo evolution's pattern, efficiency at the edge of chaos. The golden ratio marks that edge. Too ordered, and growth stagnates. Too chaotic, and it collapses. Phi defines the narrow path between the two, a mathematical balance point where complexity thrives. Which leads us to a larger question. If evolution, physics, and chemistry all converge on this number, does that mean phi is a property of nature itself, a law embedded in the universe? Or is it an emergent outcome of systems that adapt over time? Are living things reflecting the universe's geometry? Or is the universe itself alive with the same impulse that drives life to evolve? If the golden ratio keeps winning every contest evolution throws at it, maybe it's not just an accident of efficiency. Maybe it's the rulebook reality uses to decide what works. And if that's true, then we've only begun to glimpse its reach. Because when you zoom out from individuals and species and look at how life connects, neurons into minds, organisms into ecosystems, humans into civilizations, the same pattern reappears, scaled up into networks that think, move, and grow. The ghost, it seems, doesn't stop at life's design. It spreads through the very structure of connection. The ghost doesn't just appear in individual organisms, it emerges when life connects. Everything alive, from the smallest microbe to the human mind, exists within a network of cells, of signals, of relationships. And the golden ratio, the same number that dictates how leaves spiral or galaxies spin, begins to reveal another talent. It organizes connection itself. Neuroscientists have long known that the brain is not a random web of neurons. It's structured in hierarchies, loops, and modules, patterns that repeat from micro to macro scale. In 2010, researchers at the University of California discovered something strange in brain imaging data. When they measured the ratio between local and global connectivity, how neurons balance specialization with integration, the distribution centered around 1.6. Too much local clustering, and the brain becomes isolated, locked in echo chambers of self-reference. Too much global integration, and it loses coherence, dissolving into noise. The golden ratio marks the equilibrium point between the two, the moment when information flows most efficiently through the network. That same balance defines every complex system: the bronchial tree of the lungs, the arteries of the heart, the branches of a river delta, all grow according to recursive splitting rules that minimize resistance and maximize distribution. The optimal branching ratio, confirmed by fluid dynamic models, hovers between 1.6 and 1.7, a golden compromise between spread and stability. It's the same pattern found in the vascular networks of plants, where each new branch divides in proportions that maintain consistent flow while conserving material. Phi, once again, governs efficiency at the edge of chaos. But the story gets stranger. When mathematicians model network topology, the geometry of connections, they find that many natural and artificial systems evolve toward small world networks, where most nodes are locally clustered but still connected by a few long-range links. This balance produces rapid communication with minimal cost. The optimal ratio between clustering and path length, near the golden ratio, it's as if the universe has a preferred way of wiring complexity. Even human societies seem to unconsciously mimic it. Studies of social networks show that the average ratio between an individual's close relationships and extended acquaintances approximates phi. The more tightly this ratio is maintained, the more resilient and dynamic the community becomes. Too few connections and innovation withers, too many and stability collapses. Phi isn't just mathematical beauty, it's social survival. Markets show the same pulse. In financial systems, traders and algorithms map fluctuations using Fibonacci retracement levels. Not because the universe knows economics, but because human decision-making, fear and optimism move in waves that mirror natural feedback cycles. Stock price corrections and rallies often oscillate near Fibonacci ratios, 38%, 61.8%, 161.8%, the same proportion seen in biological growth. The markets breathe to a rhythm older than money itself. When data scientists mapped the internet's architecture, they found a similar scaling law. The distribution of node connections follows a power curve that mirrors Fibonacci dynamics. The web is a living organism made of information, and like any organism, it grows along paths of least resistance. As servers multiply and traffic routes optimize, the network's efficiency stabilizes around golden proportions between hub density and peripheral reach. We didn't design it that way. It emerged. The internet evolved the same way rivers branch and neurons fire, seeking balance between locality and reach, structure and chaos, cost and connectivity. Even the planet's ecosystems follow the same geometry. When ecologists analyze food webs, networks of who eats whom, they find hierarchical ratios between predator and prey populations that cluster near Fibonacci intervals. Each trophic level supports roughly 1.6 times as much biomass as the one above it, maintaining equilibrium in energy flow. Disrupt that ratio and ecosystems collapse. Whether it's plankton in the ocean or wolves in Yellowstone, stability lives within golden boundaries. This pattern repeats so often it's hard not to wonder if life has stumbled on a universal blueprint for connection. The golden ratio describes the ideal compromise between redundancy and efficiency, between order and freedom. Too little structure, and networks disintegrate. Too much, and they fossilize. Phi defines the threshold where communication thrives, in neurons, rivers, cities, and the web itself. But the deeper implication is more haunting. Perhaps consciousness itself arises from this balance. When neuroscientists measure the oscillations of electrical activity in the brain, they find golden relationships between frequencies. Gamma waves, around 40 Hz, and theta waves, around 6 to 7 Hz, interact in nested rhythms, their ratio hovering close to 1.618. This phenomenon, called neural cross-frequency coupling, is thought to synchronize distant brain regions into unified perception, a harmony of local computation and global awareness. In other words, the golden ratio may literally be the rhythm of consciousness. That rhythm extends beyond biology. In 2022, physicists at the University of Vienna demonstrated that self-organizing Bose-Einstein condensates, ultra-cold quantum systems, produce oscillation ratios close to phi when transitioning between stable and chaotic states. The golden ratio appeared, uninvited, at the border between order and disorder, the same border where living systems flourish. Everywhere we look, from neurons to networks, the pattern recurs. The golden ratio marks the threshold of coherence. It's the point where systems are complex enough to think, flexible enough to adapt, but stable enough to persist. If we accept that, then the emergence of intelligence, of minds, of societies, of technologies, is not random at all. It's the universe following its own geometry toward higher forms of self-organization. The golden ratio, in this view, isn't just a rule of proportion. It's a law of emergence. Wherever information flows and feedback loops form, Phi waits, quietly ensuring that complexity can grow without self-destruction. And that brings us to the most unsettling question of all. If the same pattern governs both atoms and galaxies, both cells and civilizations, then maybe the golden ratio isn't just a coincidence of evolution or physics. Maybe it's the skeleton of reality's code, the mathematical ghost that structures not only how life grows, but how life connects, thinks, and becomes aware of itself. Because if consciousness arises from this balance, if our very thoughts are scaled by physics, then every neuron firing in your brain right now is echoing the same timeless pattern written in the stars. We've traced the pattern from atoms to galaxies, from the curve of a leaf to the rhythm of the mind. The same ratio, 1.618, threads through it all. But now comes the part that mathematics can't explain. Why does it keep appearing? There are two schools of thought, and they couldn't be more different. One believes that mathematics is discovered, that numbers, patterns, and proportions exist independent of human thought, waiting to be found like fossils buried in reality. The other argues that mathematics is invented, a language we created to describe the world, no more fundamental than music or poetry. But the golden ratio refuses to sit comfortably in either camp. It behaves like something we discovered, objective, universal, immutable, and yet it also seems to shape our perception of beauty and order, which feels deeply human. Maybe it's both, or maybe the distinction itself is an illusion. In 1960, physicist Eugene Wigner wrote an essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He confessed that he couldn't understand why abstract equations dreamed up by humans so often predicted the behaviour of nature with eerie precision. Maxwell's equations, written in the 19th century, perfectly describe electromagnetic waves discovered decades later. Einstein's relativity predicted the bending of light years before we could observe it. Time and again, math knows before we do. Wigner called it a wonderful gift we neither understand nor deserve. The golden ratio is the purest example of that mystery. It begins as a number, a static, lifeless abstraction, and yet it reappears in the structure of living things. It's as if reality itself is written in mathematics, and life is simply the part of the universe that has learned to read. Plato believed in a realm of perfect forms, timeless geometries that cast imperfect shadows into our physical world. Perhaps the golden ratio is one of those forms, a bridge between the ideal and the real. When matter organizes, when growth and gravity play their endless game, they follow this hidden geometry not because they must, but because it's the shape of harmony itself. But there's another, more grounded way to see it. The evolutionary argument says the universe doesn't care about beauty or numbers, it cares about efficiency. Phi emerges simply because it's the optimal solution to recurring problems, how to pack, grow, and balance forces. It's not destiny, it's selection, the same principle that makes rivers find the shortest path to the sea and neurons find the most efficient routes between synapses. The golden ratio is what happens when nature does trial and error for 13.8 billion years. Yet even that explanation leaves something unresolved. Efficiency explains how the pattern appears, but not why efficiency itself feels like beauty. Why do we, the descendants of random molecules, feel awe when we see the spiral of a galaxy or the symmetry of a shell? Why does our biology recognize itself in the architecture of the cosmos? Some physicists think the answer might lie in information itself. Theoretical cosmologist Max Tegmark has proposed what he calls the mathematical universe hypothesis, that the universe is mathematics. Not that it follows mathematical laws, but that it literally consists of mathematical structures. Under this view, the golden ratio isn't something the universe obeys, it's part of the universe's identity, as intrinsic as energy or mass. Phi isn't a coincidence, it's a coordinate. If Tegmark is right, then everything, galaxies, atoms, life, thought, are all expressions of one underlying mathematical object unfolding in time. Existence, in this picture, is computation. The golden ratio might simply be one of the parameters baked into the program, and yet even that modern cosmology echoes something ancient. Philosophers from Pythagoras to Kepler saw the universe as a harmony of numbers, a cosmic symphony. Kepler called the golden ratio a precious jewel, believing it revealed God's geometric fingerprint on creation. Today we might call it the anthropic principle, the idea that the universe's laws must allow for beings like us to exist, because we're here to notice them. If the ratio between chaos and order weren't so precise, matter wouldn't coalesce, stars wouldn't form, and life wouldn't evolve. Phi might not just be beautiful, it might be necessary. Still, that necessity doesn't explain its reach. Why should a constant that optimizes sunflower seeds also describe energy ratios in quantum systems, or the oscillations of brainwaves? Why should one number weave through systems that share no mechanism, no communication, no lineage? Roger Penrose offered a clue. He spoke of three worlds: the physical world, the mental world, and the mathematical world. The physical gives rise to the mental. The brain produces consciousness. The mental gives rise to the mathematical. Our minds discover patterns and laws, and somehow the mathematical gives rise to the physical. Those laws shape the universe that made us. Each world births the next, in a circle without beginning or end. The golden ratio might be one of the few things that passes through all three: physical, mental, and mathematical, and unchanged. That circle raises another possibility, one both exhilarating and uncomfortable. What if what we call the laws of nature are not external commandments, but emergent properties of a self-reflecting system? What if the universe, in some sense, learns, refining its own structure toward harmony, complexity, and self-awareness? In that case, the golden ratio isn't a blueprint imposed from outside, but a feedback signal, a metric of balance that evolution, physics, and consciousness all converge upon. And if so, we might be living inside a kind of self-organizing equation, a cosmos fine-tuning itself toward elegance, because elegance endures. From that angle, phi is not a coincidence of physics or biology, it's a byproduct of the universe's desire, if we can call it that, to persist and to know itself. Some thinkers take this one step further. They ask, if the universe's rules look so much like code, could they be code? The simulation hypothesis suggests that reality behaves like a computation because it is one. If that's true, then phi might not just be a law, it might be a signature, the mark of efficient programming written into every level of reality, a golden watermark left by the architects of existence. But whether you imagine those architects as gods, algorithms, or natural laws, the result is the same. The golden ratio keeps showing up because it is the most efficient path between chaos and order, the line along which reality balances itself. Perhaps the question isn't why the golden ratio appears everywhere, but why anything else would. Because when you trace it from galaxies to DNA to consciousness, you begin to see that phi isn't just a pattern in nature, it may be the pattern of nature, a universal grammar written in space, time, and mind alike. And as with any language, the more we learn to read it, the more we suspect we're not the first to write in it. Remember the sunflower. At the beginning of this journey, we stood before a spiral of seeds and counted. 34 one way, 55 the other. Simple arithmetic hiding divine precision. But now, after tracing this pattern across galaxies and genomes, we can see the truth hiding in plain sight. Life doesn't build randomly, it counts, and perhaps it can't count any other way. That sunflower, that shell, that galaxy. They're all chapters in the same story, a story written in ratios instead of words, geometry instead of grammar. The golden ratio isn't just a curiosity we find in nature, it is nature, the blueprint of growth, the geometry of persistence, the quiet mathematics of becoming. Every cell, every wave, every spiral follows the same invisible law: grow, but stay yourself. You're part of that same law. Your DNA twists through space by its rhythm. The branching neurons in your brain fire in its harmony. Your heartbeat accelerates and slows in fractal intervals that echo its proportions. You are built on the same equations that shape hurricanes, galaxies, and the orbiting dust of creation. Phi doesn't just live in you, it is you. So the next time you look at a seashell or a storm or a sunflower, remember what you're really seeing. You're looking at the universe performing its favourite equation. The same pattern that holds atoms together has sculpted your perception of beauty, your sense of balance, even your idea of self. You are the golden ratio observing itself. a spiral aware of its own unfolding. And that may be the final revelation of this ghost, that it was never out there in the first place. The golden ratio isn't hidden in the fabric of the cosmos. It is the fabric of perception, the interface between mind and matter, chaos and order, being and becoming. When we find it in the world, what we're really seeing is the universe recognizing its own reflection. Tomorrow, when you pass a flower, count its petals, trace the spiral in a pine cone, watch the way waves collapse into smaller waves along the beach. Each one is whispering the same quiet truth. The line between mathematics and life is an illusion. Numbers don't just describe the world, they compose it. Life doesn't build randomly, it counts. And for reasons we may never fully understand, it keeps counting in the same rhythm. The rhythm that binds galaxies to cells, chaos to order, and us to everything else. The mathematical ghost isn't a mystery to be solved. It's a mirror. And if you look closely enough, you might just see yourself staring back. If you enjoyed this journey, consider subscribing to Omni, where we explore the hidden stories of science, nature, and the universe. Every like, every comment, and every share helps these ideas reach more curious minds. Thanks for watching, and as always, stay curious.